Okay, this is 204. What is this now? Settings on the bottom right sometimes pick up. Let me see what is the settings on the bottom right. Huh? No, it still says no, so we'll just go with. This is 204, and there are section GH, GH2, and GH3, and there will be, first maybe I should show you the syllabus and explain something about how the course is organized. So let me now go to the syllabus. Okay, now I will. Gee, I have to. I'm a little. Oh, all these things take a little. I have to go here. Whoops! No, I'm showing the wrong one. Gee, I'm a very clumsy man right now. When things don't go right, we're always clumsy. Let me see, what did I do? How do I show this? Why doesn't it? Oh, now do you see it? Are you seeing? You hear me now? Okay. All right. You should have it. I have been sending it out to you already, the syllabus. The thing that I need to emphasize, we are online and we're dealing with the second half of this general physics for biology students. But there will be 3 midterms plus a final. And now the midterm tests, even though we are online, synchronous, the administration says the tests have to be live. That means that you all have to be in Marshak building. on a given day. And when I had first set up the test date, I had chosen Monday, but they say for Monday, no available rooms for the live test. So I had to change it to Wednesday. And it has to be live, even though the test will be Blackboard. Blackboard randomizes the questions so that it would be hard for you to consult with one another. But anyway, the test will be live and it will be on that given day from 5 to 6 something. And it is with a proctor. I will not be there because I'm too old and I'm vaccinated, but I am not, that confident that with the Delta variant, you are fine. But anyway, you people are strong. You must have your mask on, and there will be a proctor there, and the proctor is there to be sure that you don't chit chat with one another, and you'll be still taking the randomized questions on Blackboard. Are you understand? It is not live on Blackboard. It is live in the sense that you are there live, but the tests will all be still online. You got the idea? Yeah, you'll be taking the exams from your laptop. You don't just walk in live and say, hey, give me the paper and I will, like it used to, you would then work on it. No, you are live and alive, and you are, there with your laptops. And in that designated room, I don't know whether it's MR1 or MR4 or something, they will designate a room for you and you say, okay, you have to be at Marshak building such and such room number, and you bring your own laptop and you'll be seated, scattered, with some distance, and the proctor is there to be sure that, and there will be no Wi-Fi issues, because that's why they have already made sure that everything is has enough Wi-Fi bandwidth. All right, that is the policy that the administration has given. So these are the test dates: October 6th, November 1st. Oh yeah, okay. Somehow October 6th, they say it's not available, so it has to be a Wednesday, and the rest is Monday, November 1st, Monday, November 22nd, Monday. And then the final, we don't know. Registrar will have their own strange way of deciding when our final will be. And when they announce it, I will let you know. And again, everything has to be live. All right? Are you okay? What is? Oh, the labs will also be live. The labs will be in Marshak Building 407 North. And it will start September 1st. Not today. You don't have to worry about, oh, today after the online thing that you have to immediately go to Marshak. It's from September 1st. They have not yet announced the actual lab schedule, like first week what lab it is, and 2 weeks later what lab it is. But when I get that, I will upload it. Okay? The labs will all be in person. And the labs are configured so that there can be no more than 24, because the space, they want to be sure that there is enough social distance between the different little lab setups. So there will be 24, and there will be a TA there for GH section, for GH2, and for GH3. Is this clear? Now, I have not fully, for the moment, I am working on the assumption that each test is modular. So test 1 will be on the material that we covered before. And then for test 2, it will be on the material between 1 and 2. And for test 3, it would be on reflection of light. And for the final, it would be cumulative. But for the moment, I am not sure because it depends on how this time constraint is, So anyway, there are some issues involved. I will settle it, but for the moment, there are 3 midterms and 1 final, and 10% homework. And the homework assignments are all on Wiley Plus. And you have been given all the flyers on how to register for it. And I keep telling everyone in my online classes that there will be something like, I have not, like 15 homework sets, because there are, about 14 or 15. And each one may be about 10 or 14 questions. So the total number of homework questions may be, by the end of the semester, maybe 200 something. Each will now count for a very small point because the homework only count as 10%. So if you get one question, you did not get what you consider to be the full credit, don't be so upset. What matters is that you have been doing the exercises. And if we have a video, you can see how I'm exercising in front of you. I'm waving my hand and making sure that my muscles are, getting not so, I'm getting old, but still I'm able to lift something. You need to do the exercises because when you do the exercises, your muscle is strong so that when you have test number 1, you'll be able to do well. Okay? They allow what? I didn't see what the chat was. By the way, you can say it out loud because I don't see very well. Okay, the lab components, the lab TA, he will send me a report. The lab is like pass or fail. If, for example, you never show up, then under the department policy, even if you do A+ on my tests, you cannot get a grade, you get an incomplete. Why? Because they say you didn't show up. Or you showed up, but you just doodle, daddle, whatever, you just wave your hand and you send in the lab report that actually shows that you have not done what is required, and you therefore fail that test, that lab, even though you were present. So it's like on a pass-fail basis, all right? So I encourage you to attend the lab sessions. And the lab sessions don't take that long. It's not like it will be 3 hours. I think it's what, an hour and 40 minutes of 2-hour session. So it's not that long time. So do show up for the lab. And now I'm going to come back to these I don't know about whether you need a reservation in order to get on campus, but you will find out, I guess. First, you have to be vaccinated. You have to show your vaccination, and then you'll be able to get into the building. Now, let me now also come to the issue of, do you have to purchase the textbook? No, you need to purchase access to Wiley Plus. When you access Wiley Plus, you have e-textbook. E-textbook that's available online, but it's not a loose leaf, textbook, and certainly not a hard copy. There are some people who would like to have the hard copy, then you pay, I don't know, it's quite a bit of money. But all you want is e-textbook. Then Wiley Plus, when you sign up, register, you already have access to e-textbook. Okay. Okay, now I want to come to this issue of the test dates are fixed. It's not one that it says, oh, I have an outing. I have, some other family outing that I need to go. You cannot show up. I cannot therefore say, hey, I will give you a separate test on another date. No separate date for a test. But if it is medical reason, there can be medical reasons, and you have a medical certificate that you send me to show that such and such, then I will not count that as 0. Instead, I'll just count you 2 out of 2 rather than out of 3. Okay, so each one is then worth, instead of 15%, each one is worth 22 point something percent. But now, what if the test, one of them, like let's say test 1, after each test, I will tell you what is the average. After each test, I will tell you the average. And incidentally, after each test, Blackboard will automatically say wrong for this, and it will say wrong for that. That's because Blackboard is very fussy, and I don't know if you have taken synchronous tests on Blackboard before. Blackboard only looks at the answer, and it has to be in exactly the format they expect. Where if it is, at power of 10, like 10 to the 4, then you should give the answer 3.14 E4. Then it will understand. But if you say 3.14 times x 10 to the 4, it will say wrong because it doesn't recognize it. But what I will have is a grader to go over the Blackboard scores and then look at your answer and give partial credit as it comes by, because when you wrote it down, you entered it as 3.14 x4, thinking that, or x10, super 4, then at least you will get some partial credit. So now, after the grader has gone over it, I will then tell you, oh, for test number 1, the average is, let us say, 60. Let's say that you only got 30. So then you're below average. Now, whether below average means that you are a D or a C minus, I don't know. I cannot tell. But what you need to then say is, gee, I got 30 the first time. I will now exercise more, right? If there's video, you will then see that I am actually doing a lot of dancing around here, right? I want to exercise more so that my muscle is stronger, so that for test number 2, I may get 80 versus a class average of 60. If that is the case, what I do is I will always calculate what I call a ratio, R. So I will take your second one, which is 80 divided by the 30, and I say, woo, you got a extra ratio of 2 point, what is it now? 7, right? You got an extra ratio of 2.7. I will count that as graciousness at the end of the semester, because at the end of the semester, I will still go by whatever's the numerical grade, and then I will look and say, gee, according to the numerical grade, you were the B, but because you show such great effort in improving, so that your R ratio was 2 point something, 2.7, 2.3, 2.5, I say, hey, I will now shift your grade from B to a B plus, or for your grade from B plus to A minus. You see what I'm saying? I will not give you extra credit because you come and cry to me, and you may indeed have very good family reasons, personal reasons to cry. I cannot. What I can do is, if you now, the next test, you actually do that much better, then I have thumbs up. I will say, okay, when I consider the final course grade, I will then uplift you from B to B plus, or from B plus to A minus, or from A to A plus, depending on what all the overall performance yours is. All right? There have been a lot of chats, but can somebody say what the chat is? Because I'm not good. Any questions about this now?
Professor, some people were asking if you will allow backtracking on the Blackboard tests.
Oh, yes. No, that's a very good question, and it's always been an important question. There is no backtracking. However, you have 2 attempts, and you'll be graded on your highest attempt. So you can keep track of what you have done, right? And what you need to do is to now say, gee, I wasn't sure on what to do, but when I take the test a second time, you have 2 attempts, then the second attempt, I would now know what to do. Okay? So you do not get backtracking, but you get 2 attempts. The only thing about Blackboard is it is smarter than what you think. It randomizes the second test so that what was question number 1 may be question number 6 now. So you just have to be good with your own window, and you capture, let's say, all the questions as they appear, and then you know how to sort it out yourself. All right. And the actual advice I have is, don't think that, oh, I want to immediately answer, because I will tell you beforehand how many questions there are. So you know, you can estimate for yourself that you should spend maybe 6 minutes, 7 minutes per question, I don't know, something like that, or 8 minutes per question. I will tell you beforehand, all right? And the thing is, don't plunge into it. Read the questions carefully and then answer it. And this will be true even when you are live, L-I-V-E, because when you are live, you are still using your laptop. Okay.
Professor?
Yeah.
A couple of people are asking, is the second attempt going to be live on campus within the same time frame as the first attempt?
Yes. That's right. It's the same time frame. In other words, let's say it has been from 5 to 6:15, I guess, for test 1 and test 2. From 5 to 6:15, or yeah, let's say from 5 to 6:15. So within that time period, you have 2 attempts. There are some people who just do the first attempt within 5 minutes and then they do the second attempt. Whereas there are others who actually go slow and then do 1 single attempt but complete. So you will know how many questions there are beforehand. Okay? Is that the... Any other questions?
Will there be any multiple choice questions, and are we allowed to use notes?
There will be multiple choice questions. And of course, you can use notes because after all, you have your laptop, so you have access to your e-text, the book and whatever else you have. The only thing is, even for multiple choice, you better read it carefully. Because answers to some of those multiple choice, I agree, depends on how exactly they pose the question. You know, because there are tricky ways of confusing you. And so you have to now say, are you talking about this, silly guy now doing this silly thing here? Or is it somebody conk him on the head? You have to read it. And then if you read it, then you say, yeah, it is choice B. And I will give you 5 choices, A, B, C, D, E. And some of the choices I give depends on the equation, because it may be that the equation should be x equal to 5 over 3 minus z or something like that, especially with cosines. You know, I like to confuse you with cosines and sines. And then I'll give you 6 possibilities, some with cosine, some with sine, some with plus sign, some with minus sign. And I'm very good at confusing you with extra factor of 2. And then you say, oh, I have A, B, C, D, E. But since I have myself worked it out, I know it should be C. And you then answer C. Are you following what I'm saying? Okay.
Hey, Professor, I have a question about the textbook. So I purchased Wiley Plus, but don't have access to the textbook. I purchased it for $70 and I got the access code, but I don't have the textbook, the e-textbook.
No, you don't get the textbook, physical textbook. You get access to e-text.
No, I don't even have access to e-text.
Oh, really?
Really?
Oh, is anybody else have that same issue?
I have
nobody
almost
else?
an inverse issue where like it's not allowing me at all to make any kind of purchase for a subscription. Like I registered with the code given on my syllabus, and I have it open in that regard, but I'm not actually like subscribed to anything.
Why don't you send me email? Because then all I can do is to complain to the Wiley Plus representative, because I have no administrative control over Wiley Plus.
I sent you an email, Professor. I purchased Wiley Plus through VitalSource, and I was able to get the access code, go on Wiley, but there are no e-textbooks.
Maybe you have to navigate and then find there is Wiley Source or something. You then, anybody else with that same issue, because it could be that you did not navigate, because the whole Wiley Plus platform is quite confusing. It took me a long time to navigate the whole platform.
I had the same problem. I got access through your syllabus code. It didn't charge me anything, and the book's not on there.
Oh. Well, I have to...
Sorry to interrupt.
Yeah.
For the people that are having that problem, so what I did was I also, I registered and everything, and it didn't charge me, but I didn't see the book. But in order to see the book, you actually have to go to the course resources, and then go down where it says e-textbook, and click like the first link that says e-textbook. It is 16.1, the nature of waves. Click that, and then it's gonna open another link, and they want you to like create like another account for the book, and after you create that account, you put the name, the same information basically, then it gives you access to the physics book. Right,
yes. And when you create an account, they don't charge you,
but
because you have already
there.
Yeah. So did everybody hear what she said?
Yes. So Professor, I just want to clarify. So in order to just do the homework, like not needing access to the book, we don't need to pay. The paying's only for access to the ebook?
No. Paying is access to doing the homework assignment.
But I'm able to see the homework and open it, and it shows that the assignment unlocks in an hour without me having paid for it. And it's not giving me the option to pay.
Well, then you don't have to pay. I don't know, but you're supposed to pay to get the access. Maybe they have a grace period. There's a grace period, and then if after the grace period you don't pay, they kick you out. So there's no free lunch, you know. Any other questions? I know, but they keep changing their platform. It used to be 8th edition, Cutnell Johnson. Then they changed to 10th edition, and then they changed to 11th edition. And I'm told soon they go to 12th edition. And each time they have a new edition, they have totally new platform, and then they confuse everybody because the clicks are now different. But you know, that's Wiley Plus. Okay, maybe we should now go back to. If there are no other questions. Okay, if there are no other questions, let's now go to. Whoops, what do I do? Okay, how do I get out of it? How do I get out of it now? I should. How do I get out of this guy? Do you see it now? Okay. All right. Let's go on now. Okay. Now we want to go on to waves. This is chapter 16. And this is all about waves and sound. When you have a boat passing by you and you are the fisherman, the lake is absolutely calm. And all you're doing is waiting patiently to catch fish. But when a boat passes by, especially these guys with a speedboat and they go 30 miles per hour, when they pass by, the poor fisherman will say, wait a minute. Suddenly, I get bumped up and down, up and down, up and down, right? The wave that's created by the motorboat travels across the lake and disturbs this fisherman. And what we are talking about in this chapter is waves and sound. And I download this picture. Yeah, you can talk among yourselves about the grace period. I think it's usually 14 days. There are these gondoliers. You know what's a gondolier? These are the guys that bring you down the canal. Venice has a lot of canals, and when you become successful, you want to go to Europe when there's no, COVID-19 issues. Then what the gondoliers complain is that there are these cruise liners. Oh, they would like to come by because they want to see Venice. And they now have these people coming by, but the big cruise liner creates a big wave and they protest. And so now I think at least the local authorities have now banned the cruise liner from coming too close to the Venice canals. They can dock somewhere and then the people can come down and then take the canal boats. Now, the same effect or the same issue is actually in this. What are these birds doing? What are they doing? They're flying, right? They're flying south. And we usually call them the Canadian geese because these are the geese that are flying from Canada and they want to now, during the spring and the summer, they come down. Well, you notice that when they fly, they always fly in a V-shaped formation. Do you know what is the physics behind it? Can somebody sort of venture an opinion? Whatever opinion you have. Can you hear me?
I'm raising my hand. Should I just talk?
But I don't see you raising that hand.
Oh, my hand's raised. I don't know what's going on.
Oh, okay. Why is it always in a V shape? Do you know?
Well, if I remember correctly, the reason it's in the V shape is in order to minimize the effort of flying. And that happens by the first bird all in the front, essentially putting up the majority of the energy to move out the wind and make the flow easier for those in the back. And once
Right.
that bird once that goose finally gets tired, it'll move back.
Yeah.
Another one that's like hasn't spent all its energy moves forward, and their cycle
Right.
repeats until they reach their destination.
Right, right. That's very good. That's a very good physics explanation. Because this poor guy, he's for the moment the leader. And man, he's got to flap the wings that much harder because he's got to basically be rowing, like the boat. He's got to be rowing the boat to be going fast, like the speedboat. And then that speedboat creates a wave, or sometimes people call it the wake, W-A-K-E, right? There's a wake from this. And these guys, when they are on both sides of it, they are taking advantage of the wake or the wave that this leader is doing. So the leader is, I don't know how the Canadian geese, do they go, whatever, right? So they are flapping. The poor guy, he is flapping. But after, I don't know, let's say 2 hours, 3 hours, he says, I am tired. I cannot do it anymore. And then what happens is the next guy takes over. And so this guy will now move faster and this guy will come here. So that's why the V is always in the end, not the exact equal. This side gets longer and longer. Why? Because this guy will say, hey, you take over. So this guy takes over. And then this guy takes over, then takes guy. And then when it comes to more or less the last guy will say, hey, you guys, help me. I am no longer able. And then what happens is these guys will now move to the side. So that's how they are able to fly, I don't know, let's say for 10 hours or 12 hours before they rest for the evening. All right. And it's likewise when you're on a highway, when a bus is overtaking you. Have you ever noticed that? When the bus is overtaking you, the bus, it may be coming by, or they may be coming by, and they may be coming by, like, let's say 60 miles per hour, and you're also going 60 miles per hour, but let's say they go 65 miles per hour and you're going to 60 miles per hour. When they pass you by, you can feel sort of like the shock wave, right? And in fact, if you now keep at the same speed as this guy is 65 miles per hour, you're also going 65 miles per hour, but your engine doesn't have to work as hard. You will notice that. You don't have to step on the gas so much, and you are really taking advantage of the wake that comes from this bus. That's the team spirit, I call it, okay? Well, we are now studying the waves. A wave is a traveling disturbance. I have this string. Well, they have it as a spring, but I can think of it as a string. And I have nothing else to do. All I do is I just wave this up and down, up and down, up and down. You notice? All I'm doing is up and down, up and down, up and down. But when I start moving it up and down, this will now propagate down. You see, this will now propagate. Those parts of the clothesline, yeah, it's oscillating wave. Those part of the clothesline over here, they didn't know that I was waving it up and down, so they were still at rest. But these guys, they have been pulled. So they pull, and then as they pull, they let the neighbor know, pull, and then at some point you have stopped pulling up, you are pulling it down. So what happens is they go up and come down, and they go up and come down, and go up and come down. So this now becomes a traveling wave. Do you see this picture? You must have played with it as a kid, right? You know, when you're, it used to be you don't have a clothes dryer, and so you have to hang it out to dry, and then kids can play with a string tied to a tree somewhere, and you can actually have this transverse. This is called the transverse wave. It's transverse, okay? All right, this is called a transverse wave. There's also longitudinal wave. Here is your spring. It was originally natural length, but you, being a little kid with nothing else to do, all you do is you begin to push. Now, when you begin to push, oops, my battery is getting low. Now, when you start to push, then this part of the spring is compressed. These guys still say, what's wrong? Nothing. But now, and this is compressed, but then you start pulling it back. This is now stretched. This is now stretched. This is compressed. And then this compressed is now compressing the others. And because it compresses the others, it now becomes stretched more. And you have stretch, compress, stretch, compress. And that is what you call a longitudinal wave. All right, do you see this picture? And now we have water wave. Water wave is a combination of longitudinal and transverse. It's longitudinal because the wave is coming ashore. You are at the shore and the waves keep coming in, and at some point we will be interested in what is the frequency of the wave at the shore. While we're at it, maybe somebody can help me. What is the rough order of magnitude of the frequency of the water wave crashing on the shore? Is it every hour? No, right? What is it, roughly? You're a biologist, but you also go to the beach, right? Yeah, every minute, or actually it's every maybe 5 seconds, 10 seconds. It all depends on the weather condition. Yeah, every few seconds. It all depends on the weather also. Because if you're at the beach, and now there is a Henri coming by, yes, when there's a lot of wind associated with Henri, would the wave still only come by every 6 seconds, every 10 seconds? Or would the wave now begin to be every 3 seconds, every 2 seconds? Yeah? So the wind is blowing the waves. So there is a forward motion of the wave. But if you now ask the water, each water, are you actually now moving with the wave? What happens is the individual water is actually going up and down, sort of like in a circle. It is a combination of motion to the side and the combination of just up and down, transverse. All right, there's a longitudinal and there's a transverse component of this water wave. Do you see roughly now this picture of what is a water wave? If you have a tidal wave from the middle Atlantic, it does not mean that all the water in the middle of the Atlantic is now running to Long Island. It's only that the water in the middle of the ocean, it's going in a circle, but this circle affects the neighboring water molecules, and so it actually becomes a water wave that carries energy from this to here, to here, to here, to here. All right? So roughly you have a sense. You can have purely transverse, you can have purely longitudinal, but you can have combination, which is this water wave. And speaking of water waves, oh, right, and now here, these are waves that carry energy, where energy is carried from here to here to here to here. There are some, I don't know whether you want to call it a fake wave. What I mean by fake wave, have you ever been to a stadium where they arrange it so that people put a, by arrangement, let's say wave a card, you know, right? And then what happens is you see a wave which seems to run from the left field and it goes up and down all the way to the right field, so that it is as if it's a wave that is traveling. But it is fake. Why? Because the people are not running from the left field and the seats, they are not running from the left field all the way to the right field. All they're doing is standing up and down, but in some coordination. You follow? I mean, I got this downloaded somewhere. You can see each guy, all they do is just up and down, right? But they have a certain coordination so that it looks like, hey, there's a wave. This one is not such a good picture of what I want to show in a stadium where people, in fact, have coordinated so that it looks like it's a wave, right? Yeah, okay. So I just wanted to show you different kinds of waves where there is true energy being carried across versus some of these fake waves. All right, but now what we want to now do is to look at these so-called periodic waves. They are waves that go in a definite frequency. It could be every, the period. By the way, period and frequency, they're inversely proportional. If I have 5 hertz, namely 5 cycles per second, then the period is 1/5 seconds. Namely, in 1/5 of a second, it has gone through one period, and in 1 second, it then has gone 5 cycles. So this is then an example of periodic wave, and it had a particular frequency, and this longitudinal one also had a particular frequency. And now for the description of periodic waves, we now need to have a certain language. And the language is you need to know the amplitude. And the amplitude is the displacement from its equilibrium. Namely, if there was no wave, the string would be here. But because of a wave, it went up by A, went down by A, went up by A, went down by A. So the amplitude is the displacement from the equilibrium. And this is what you call A, all right? Amplitude. And then the wavelength is the distance from, let's say here, 0 to the next full 0, because this one, it went up and then came down some more and then came back up. Then this distance is called the wavelength. It's the actual distance from the top of the wave to the next top of the wave. That is one wavelength. Or the distance from the trough, the depth of the wave, to the next depth of the wave. That is lambda. All right, that is the wavelength. The period, is the time required for one complete cycle, and that's related to frequency, as I said. Frequency is inversely proportional to the period, and frequency has the unit of hertz. It's H-E-R-T-Z or H-E-R-Z, I don't know. I'm not it's a German word, hertz, named after the German physicist Hertz, H-E-R-T-Z. Not the Hertz rental car, but Hertz. Yeah, thank you. It's not the rental car, it's the scientist, German scientist. Okay. And now I want to deal with a wave which is important because it is so contra-intuitive, and it actually affects you and all of us when you're vacationing in a nice, I don't know, island somewhere, and you say, oh, such a beautiful day. I lie down on my beach and I'm admiring the sky, right? And meanwhile, there is a tsunami. Have you ever heard of this word called tsunami? You have not heard of the word tsunami? Of course, yes, thank you. And now, what is the most important thing about tsunami? The tsunami has nothing to do with the weather. You can be lying there, enjoying the whole beach, enjoying the sun, and you say, oh, it's a beautiful sky, and I, paid so much money to come to this vacation resort area, and I'm enjoying it. And meanwhile, this earthquake occurred somewhere else. Earthquake did not occur at your beach. Earthquake occurred somewhere else. Somewhere else? It could be as far as 6,000 miles away. The earthquake could have been 6,000 miles away. And you say, I didn't feel any earthquake. And yet, that tsunami wave, when it comes quietly. It's not like, when Henri came by. Man, I don't know if anybody would stay on the beach when Henri was, howling by, because the weather is bad and you better run. But for tsunami, the weather is beautiful. And yet, there is this tsunami wave coming. And now, what is this tsunami wave? It's the Japanese word. I know, that's very scary. And I want to impress on you, be careful, right? Tsunami wave is the harbor wave. That's because Japan has a lot of earthquakes. And there are many tsunamis that are formed due to the fact that Japan is on the ring of fire, where the earth underneath, there are always what they call tectonics. That the plate, whatever is the plate for this part of the earth versus this other part of the earth is pushing each other. And when there is somewhere an earthquake that is due to this one pushing itself under, then it pushes up the water. And this is in the ocean. And it pushes up the water. And so the water now is lifted up. And now when the water is up, it could be lifted up maybe 3 feet, could be lifted up 5 feet. But the water that is lifted up, you're talking about an ocean where the water is, I don't know, let's say 100 feet deep or bigger than that. So all of that water is lifted up. Where does the water go? It's like a bathtub. If you now lift up all the water in the big bathtub, they will just overflow. They will now start flowing away from the fault line. And you will now have a tsunami wave on this side of it going to Japan itself, or into Pacific Ocean, and on this side of it going into Japan. So this is tsunami wave, and Japan has had so many tsunami waves, so they actually have tsunami alert. They actually have, alerts at all the coastline, and when there is a earthquake that actually does produce a tsunami, they will then tell everybody, run. They will tell everybody, run. And one safe way to run, if you're on a boat, is to go out into the ocean. Open sea wave is fine. It's just you go up and down. But if you are now on the shore, be careful. If you're on the shore, be careful. Why? Because this tsunami wave is coming. It is a pile of water, and now your ocean floor near the beach only comes up, meaning down here it may be 100 feet, but down here is now going to be 60 feet, 30 feet, or just 5 feet, and all of that water now is going to pile up. This amount of water is going to pile up, and so the wave height can be, they say, 12 meters. When it is 12 meters, you know how many feet that is? It's about 40 feet. Huh? Is that scary? And you don't hear any thunder, you don't hear any sound. All you see, you may not even see it because you're lying here, you're looking upward, admiring the sky. This tsunami wave comes, and then at some point, this wave breaks because it has the velocity, it is now breaking. And when it breaks, that's when you hear the sound. But then it's too late. And now there's a very famous tsunami. It's very famous because I'm from Singapore, which is the red dot at the bottom of Malaysia. And I think I was there in 2004. And it happened December 26th, morning, local time, in just outside Sumatra. Right? So here is where the epicenter was. And this tsunami is earthquake of 9 point, I think the next one will show, 9.0. It's an earthquake of 9.0. The recent one in Haiti was what? Do you remember? 7.2. And it already caused a lot of damage, yes? I'm not looking down or belittling the disaster in Haiti, but I'm saying there was an even bigger one in 2004, and it was 9.0 earthquake. And that created a seismic wave, which then, a tsunami wave, which then traveled across the Indian Ocean. And it went all the way to Africa. You realize how far that is? And now, here is the most important fact about tsunami wave. The tsunami wave, its velocity is 550 miles per hour. You know what does the jet plane go when they fly, when you fly across the continent? The jet plane goes 550 miles per hour. All right? So the velocity of the tsunami wave is fast. And the wavelength, oh man, is 150 miles. People have measured, because people worry about tsunami. People have measured a tsunami wave, the wavelength is 150 miles. Therefore, the frequency or the period is 16 minutes. All right? Now, why is it so frightening? That's because here you're on the beach, and let's say that, oh, there was a big crash, right? And you now, whoop, but thank God I survived. Yes, I survived. Now, there is one Phuket, Phuket, which is in Thailand. I've never been there, even though I, was born in Singapore. But there are people, especially around Christmas time, people who came from Denmark. There's one particular tourist. I don't know his name. I wish I had recorded it somewhere. He was on the beach in Phuket, and there was this tsunami wave, and it crashed, but he survived. He was a young man. He survived. But then when he survived, all the local people says, "Get out, get out, get out." But he saw that there were other people who were, knocked out. So what did he do? He went to help pull those other people up to the higher ground, right? So he did that. And to him, it looked like, well, after one such big wave, nothing happened. For 16 minutes, it looked like, it's peace again and quiet. So he was helping to move. And then the second wave came. But he survived again. And he, instead of now saying, "Ooh, I better learn, I better run," what did he do? He continued to pull those others who were, affected. And then the third wave, he did not survive. And to this day, somewhere there's a memorial to all the victims. Do you call them victims? All the people. Do you call them victims? Yeah. I mean, it's not because somebody knocked them on the head, but victims of the tsunami wave. And in Phuket, they have somewhere a memorial. It's sort of like Vietnam War Memorial, but it's not of that kind. In Phuket. So just the warning is, be careful. If ever that happens, and it does, you were involved in it and you survive, you better run to higher ground. Okay? All right. So now that we have already set up this, relationship, and the most important relationship for wave is this relationship. Wavelength. Relationship with the velocity of that wave and the period. Because if this is the wave, the train that is passing by, and it is coming at a certain velocity v, then I know if the period is t, then in a cycle, v times t is the wavelength. So this is now the definition of the relationship between wavelength, velocity, and the period. Or I can write this as the velocity of a wave is frequency times wavelength. All right, so this is the fundamental relationship which we had already used for tsunami wave. Okay, and now we can apply it. And the book applied it to radio waves, AM and FM radio waves. And they say, well, AM and FM, radio waves are transverse waves consisting of electric and magnetic field traveling at the speed of light. We will come to the chapter on the wave nature of light, and then we will they address it again. But here, they just want us to have a sense of the scale, all right? And first, we all are familiar with AM station. I don't know what's your favorite AM station. You have so many different stations. And the broadcast AM station, they will tell you it is so many kilohertz, right? It's actually not kilohertz. It's 1.2 megahertz. Or actually, they call it in kilohertz because they say 12:30 AM, you know, right? Whatever the name of the station, they will say it is 12:30 on your dial, on your radio dial, right? AM radio dial. And it is in units of kilohertz, and it is 12:30, or FM station, where it is now 91.9 megahertz. And you will say it is 91.9 on your FM station dial. And what you can now ask is, what is the wavelength difference between AM and FM radio waves? Right? I mean, this is a simple application of this simple formula, but it is very interesting because we will then recognize the difference. So for AM, they say, oh, you are told it is 12:30 on your AM dial. It's 12:30, but it is kilohertz. And we know that the radio waves are the velocity of light, which is 3 × 10⁸ meters per second. So if you work it out, the wavelength of a AM station broadcasting wave is 244 meters. If you now say, well, what about my FM station? FM station, the frequency is 91.9 megahertz. So they'll say on the radio dial, on your FM radio dial, it is 91.9. And then you'll be interested to know, what is the wavelength of that FM station wave? It is 3.26. And now you know what is the difference. You know what's the difference? Or why there is a difference? Do you know the difference between AM station and FM station in the quality of the broadcast? Do you know the difference? Yeah, you know what's the quality difference? You see, if I am a FM broadcast, my wavelengths are 3 meters, and now I am in New York City. FM is significantly better quality, yes. FM is significantly better quality, but now the thing is, the reason why it is more significant quality is the frequency is higher. The bandwidth is higher. You see, it's megahertz, 91 megahertz, whereas the other one was only 1.2 megahertz, right? So FM wave, broadcast wave, they carry a lot more bandwidth, and so the quality is much higher. You know, when you want to hear a stereo music and you want to see, you know, hear the concert, oh, it is so very, like I said, you are live. But the wavelength is 3.26. And when you are in New York City, the buildings, the waves, they easily get interference. You know, my wavelengths are so short. The fact that you have a tall building along the side to my radio as my car goes, and I'm driving in, 42nd Street, 135th Street, and I'm on FM radio, there can easily be interference because Marshak building interferes with the path between where the tower of the broadcast tower is, transmission tower is, to my car. You see what I'm saying? So I am driving and I am receiving the signal, as I'm passing by Marshak Building and as I'm passing by Empire State, the transmission tower, the site to the transmission tower is now blocked. There is interference. But an AM station, oh, it is 244 meters. So it is longer and therefore less affected by Marshak Building, because this is about 800 feet, 1,000 feet. So AM stations, the bandwidth is smaller, but it is not affected as you're driving. But FM station, oh, they are much more easily affected. All right, I just want to point out the difference between a wavelength that is so small versus a wavelength that is much longer, almost 100 times longer, but the quality-wise, you have much more bandwidth with FM than with AM. Okay, so now let us get to some math here. So far, the only math equation we've been dealing with is V equal to lambda F, right? That's the big formula after all of this discussion. Now we want to deal with a little bit on the mathematics description of a wave, a periodic wave. And so the first thing you look at is this is a traveling wave, and this, look at it as a transverse wave, and you now look at this as a function of x, right? This is my clothesline, and I see that there is a wave traveling along my clothesline, and I now plot it. I follow it. So first, I just say, I want to know what is the distribution of this displacement as a function of x at the given time t equal to 0. Right? Say I'm not interested in later time. I'm just looking at it as here. I have this wave, and I like to know this displacement y as a function of x. Well, I know as a function of x, it will go up and down and up and down because there's a certain wave going through it. And it will be such that when x is one full wavelength, y again will be 0, right? When x is a full wavelength away, y will again be 0. In between, oh, y will become negative here, become positive here, and then become 0. So I know when t is 0, it would be sine kx, where k is 2 pi over lambda. Let me see if I can say it down here. At t equal to 0, I know y is a sine 2 pi x over lambda, such that when x is lambda, sine of 2 pi is 0 again. So this is then the formula for describing this wave, this transverse wave, as a function of x. All right? So I know when t is 0, it should be sine kx, where we now say k is 2 pi over lambda. But now we want to know what is the correct description of this wave when it is at later time. Well, at later time, I know if at later time, the place where this thing is a node, N-O-D-E, namely where y is 0, it will now move here and move here and move here at later times. You follow what I'm saying? This point where it is a node, N-O-D-E, this node will travel with time. And it will travel with time according to what is the period of this wave. So that when it is now at the later time, it will be 0 here. Later time, y will be 0 here, later time y will be 0 there. In other words, at later time, it should be x minus vt times k. Meaning, when x is equal to vt, because it is going with a certain velocity, this node is traveling with a certain velocity, then sine of 0 will always remain 0. So if I now recognize that this formula, if I want to generalize to include time, then I should make it such that sine of this position x equal to vt, that this position for the node, it would always be 0 at later time because this node has traveled with a certain velocity. And when I now re-express this or write it out, I remember that v is lambda f, and then I will have kv, but kv is omega. I better write it out here. I will notice that kv is 2 pi over lambda times v, which is lambda f. So therefore kv is omega. All right? Where omega is 2 pi f. Oh. And so, therefore, the general formula is this. Are you okay with this? I mean, my scratchy handwriting is not such good. You got it? Yeah. So we now have a general formula, and you are not going to be a engineer. You don't have to worry about too much, but it's good to know which formula to use for whatever they may be interested in asking you. So you need to know, for a traveling wave, the general form for this displacement is kx minus omega t, sine of kx minus omega t, where now we introduce the wave number called k, and we call this angular frequency, because f is frequency, but omega is now angular frequency, and its dimension, its unit is radians per second. And k is inverse. It's called the wave number. It's the inverse meter in units, right? Any questions? Okay, all right. So now we want to come to sound wave. Sound wave is very important, because without sound wave, you wouldn't hear what I'm yelling at. I am speaking, I am yelling, well, not exactly yelling, but I'm speaking loudly. And this, my laptop has a microphone, and it absorbs the sound wave, and then it now, by the electric circuit, transmits it into electrical wave by the current to your laptop, and then your laptop now has a microphone, and it now transmits that out into the air, and then the sound wave goes from your laptop microphone, loudspeaker, into your ear. So sound is very important, and we all need to know that, because for our daily life, the issue is, do you hear this? If I keep calling, you don't hear it, something is wrong. If we were on the moon, I can yell all I want to. You can never hear me. You can yell you want to. I can never hear you. Why? Because there's no air. There's no air between you and me in the moon. But over here, there is air. I have air in my room, you have air in your room, and that's how I'm able to, even though you can't see me, you can hear me. All right? And now, sound wave is like a spring. You have compression because the air is being compressed by this drum, because this speaker is a drum. Well, it's being compressed, and now there is compression, decompression, compression, decompression. So that's how the sound is propagated. And that's how you get individual air molecules. Oh, they are now compressed, decompressed, compressed, decompressed, compressed, decompressed, and they come into your ear, and then your eardrum is being compressed, decompressed, compressed, decompressed, and it then translates into our brain. And now a sound wave, well, you have frequency, the various tones. I mean, these are for the handphone, they have different frequencies, and you can tell from the phone. For some of these phones, you can tell who is calling you. Although I have not said it that way, but some people with a cell phone, they can tell who is calling because they have already put their favorite one with a particular what they call it, sound, right? Have you been able to do that? Are you able to when a phone is ringing? Yeah, ringtone, right? Yes, you know, right? Some people have ringtone that says da 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 da, and then they know it's their loved one calling. And if it is dong 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 dong, then they say, oh no, it is some unknown guy, right? But anyway, you have a lot of these, and they all come from the sound by compression and decompression. And for us, there are two issues that are very important. One is the speed of sound. We're not going to go into that part of the book. The book also tries to give you the technical formula for the relation of the speed of sound to the tension. You know, we will not. I'm not interested in that. Engineers are interested in that. I'm not. What all I am interested in is what is the speed of sound in air. And it is important for us to know it is 330 meters per second. That's a very important number because it tells us when I'm speaking how fast the sound goes from me to the computer and how fast the sound microphone, the speaker on your phone travels to your ear. It's 330 meters per second, which is very fast. But now for liquid, the speed of sound is even faster. It was 330, this is almost 5 times faster. Yes? And what is more is the speed of sound on metal, on steel, on copper. Oh, it is even faster. This was 330 meters per second. This one is 6,000 meters per second. So it's almost 20 times faster. That's why when you want to complain to the neighbor, I don't know if you ever complain to your neighbor. It is not, let's say, you can yell all you want to, sometimes because of the asbestos and so on, people don't hear you yelling. Although there are some buildings where, you know, whoever yells, you can hear. But there is sound absorption. But if you knock on the pipe will transmit the sound 6,000 meters per second, much faster into the next room and to the rest of the building. Okay? So just be aware that there is the speed of sound and you can now have a very important application, which is important for you and for me and for everybody else. This application has to do with the fact that you are, well, do you play golf? I guess you don't play golf. I don't play golf either. But you're on a beach. You're playing volleyball. And you want to finish the game. And you hear this rolling thunder, you know, right? You hear a rolling thunder that comes after the flash, you know, like you see some flashes and then a few seconds later you hear a rolling thunder, right? Right? And you say, oh, no, let us finish this game because, you know, I'm almost going to win. Be careful, because you need to now know when you have this lightning and then you hear the rolling thunder a certain number of seconds later, how far is the lightning? How far is the cloud? And then later in, I don't remember now which chapter, we will in fact be talking about this reason why there is this lightning and how the electrons, they are you know, searching everywhere for a positive cloud coming by. And if you are standing up here, all the electrons want to rush through you to go to the cloud. And when you are standing up here, when the cloud is coming by, thunder cloud, lightning cloud is coming by, be very careful. Lightning can strike you. All right? We will come to that when we come to that chapter. I don't remember what chapter it is. And so here is a very simple application. They're just simply saying, hey, what is the rule? If I hear the thunder t seconds later, it could be I hear the thunder, you know, 5 seconds later, right? If I hear the thunder 5 seconds later, how far is the cloud? Well, you know the distance is velocity times time, the period, and the velocity, the speed of sound in air is 330 meters per second. And then this t is whatever, whether it's 5 seconds, whether it's 10 seconds. And now you want to convert this meters per second into miles. Well, we go by what I call the horse and buggy way, which means that you now convert 1 mile and kilometers. 1 kilometer is 0.62 miles. So therefore I write this as 0.62 over 1,000 meters, because 1 kilometer is 1,000 meters. And if I now do it this way, I cancel the meter. I now have so many miles per second times t in seconds. So therefore the rule becomes, whatever is the period, the time that you hear the thunder, the actual distance is the time divided by 5. If it took 5 seconds, I heard the thunder 5 seconds after the flash, that means that this cloud is 1 mile away. If I hear the thunder 1 second after the lightning, be careful, it's only 1/5 of a mile away. Are you following me? It's a very good rule of thumb. It's a very good rule of thumb for anybody who is either on the golf course or on the beach playing volleyball and so on, that beware. When you see a flash of lightning and then you hear the thunder, and you better count 1001, 1002, 1003, then you will tell you it is 3 seconds later. That means that this cloud is 0.6 of a mile, half a mile away. And if you hear the next roll, the thunder is after the next flash, the thunder is 1 second later, man, it is really 1/5 mile. Don't keep playing the volleyball. Don't keep swinging the club for the golf course. All right. Well, what are the chances of this ever happening? it is, let's say, it's not one that when the thundercloud is over you and you are so happy and you put your golf club up that you will get it, because the cloud is quite big. There may be somebody else who has higher than you, and then he or the tree got hit by the lightning. So it does not mean, but you're exposing yourself to, because what you're doing is you are now having your golf club up, and the electrons now come up to the golf club, and the other electrons, because the cloud is so big, maybe over there it is not as high, then it is your electrons that are over here that go they go zoom across, and that's when you get your lightning strike, right? So just be aware. And it has happened. Don't think that it never has happened. It has happened that people on the golf course, it has happened that people on the beach got struck. Yeah, I don't know what this but okay, all right. So now we want to deal with a very important subject, which is intensity, because we have been talking about speed of sound, we've been talking about the frequency. Well, an important, oh, that was your cat. Okay. Your cat got electrified. Okay, all right. So now we want to deal with a very important subject, which is intensity, because that has a lot to do with our health, our life, is we're able to hear. And the intensity is the amount of power that passes by over the area. Because here is the speaker and it is emitting a lot of sound energy, and the intensity is the power, so many watts divided by the area. Okay, well, so now they say, hey, you have a speaker and it gives you this much sound power, and they are giving you the numbers that have to do with actual science. So the actual power of a sound coming out from a speaker at so many watts is so much sound power, and you want to now know what is the intensity. If you are very close to it, you get much more effect by that sound than the guy which is further away, right? If you are at a concert and you are really near the stage, you got to be aware that you are your ear is subject to a lot more, sound wave impact than a guy who is, further away. And they give you some examples. Oops. They give you some examples when you're only, what is this? 2 meters away versus square root of 12 away. So it's 3 meters away. So you can tell what is the intensity. The intensity of this guy is less. You are very close to the speaker, to the stage, you will have a lot more sound wave hitting your eardrum. Okay, so now let us go on, because we are getting almost to the end. We want to finish this. So here, this is a formula which says that if I know how much power is coming from here, then the intensity is the power over the surface area, which is 4 pi r squared. Now here is a good, interesting application of intensity, and let me just, you can look at it later, but let me just, do you sing in the shower? Or you never sing in the shower? Or you're one of those that, are absolutely quiet when you take a shower? Now, generally you sing in the shower, right? Do you notice that when you sing in the shower, it sounds so much louder? No? Yes? Whatever you're singing, right? It's so much more enjoyable. unless you're so sad and you, you right. But anyway, the thing is, they gave you this example, but my own technical answer to them is they didn't fully consider all the issues of sound, because they say, hey, you sing, there's a direct sound, so down here it is, you will receive directly, but down here you also receive the reflected sound, right? And then this reflects back to you, right? And so it is clear that you would hear more. Why? Because it is not just the sound that goes to this side of the shower back to you, it also includes the reflected one. The only technical point which they did not deal with, and it is important, is that when the surface here reflects and the surface here reflects, there is now an interference between the original sound and the reflected sound, and there can be negative interference, there can be positive interference. If you go to an auditorium, there's people who design the auditorium, they know that there are issues. You paid $50, I don't know how much, maybe by now it's $100 for a good, front row seat in a musical concert somewhere, right? And what can happen is, yeah, the opera houses, they have reflectors. They are what some of them call them clouds. You cannot see me, but they have these reflectors, and then what happens is they know that there can be some interference that cause a high C note to be canceled out, and you paid $100 and you want to hear the aria where the person starts singing like, oh, but then you hear that, oh, but then the other guy next to him says, I don't hear anything. Why? Because it was canceled out. So what they do is they now install these reflectors in order to reflect, to fill in those dead spots. And so what you then do is, when you construct or design a opera house auditorium, they ask the sound engineers to please make sure that every seat in the house will not have dead spots, that every seat people can still hear whoever the soprano is singing the notes, or the drum beats and so on. So this is just simply a very crude question that they ask, but it's a very complex question. But now, before we fully end, let me just quickly say, for us and for the engineers, the important thing is this thing called decibel. It's a measurement of your sound intensity, and it measures the intensity compared with some standard intensity in base 10, logarithm base 10. And you go by decibels, and you have, for people who are able to hear a rustling leaf, that's 10 decibel. For people who are able to hear whisper, that's 20 decibels. Normal conversation is 65 decibel. Car without muffler, 100 decibels. And threshold of pain, 130. Live rock concert, 120. This is an intensity, but it shows that the intensity is powers of 10. That compared with a whisper, it is 10 to the 5 times more intense. So this is counting the intensity by powers of 10. And just be aware that when you have a concert, or when you're standing in front of a jet engine, that indeed there is a lot of intensity that is hitting your eardrum. And I think we'll end with, we'll deal with the Doppler effect, but I wanted to show the eardrum, because before we end, we would Oh, tornado, don't worry. The eardrum. Where's the eardrum? Oh, okay, all right. We'll see you next time, and I will have the eardrum because it is a fantastic, thing that we are able to hear because of this eardrum that can actually distinguish between powers of 10. Okay, all right. So sorry we went too fast. Okay, see you on Monday. Bye. Bye. Yes. Okay, all right. Oh, I should stop the recording.